Hey, so I'm looking here at number 82 from section 11.1. It's kind of related to the problem that you all are assigned in 80, and so I want to give you some thoughts here. So for this one, we're considering two people who are carrying a 100-pound weight, and each of those images here corresponds to a rope that each person is holding. So one rope is coming off here, which is 30 degrees off of the vertical, and the other one here is 20 degrees off of the vertical. The way I've drawn it, the 20 likely should have been longer and a little bit steeper. But hey, sorry about that. It is a little bit more like that in the image in the book. Now, what I disagree with the image in the book that I would change is I prefer to imagine the force that they're exerting. Right, they're pulling it up. And so this F2 and F1 could be the force that they are exerting, although it is equally matched. Maybe if I call this like big F down here, big F, the arrows that they drew corresponded to the way big F was given to the other two ropes. But because the questions here correspond to the tension when the resultant force is vertical, and the vertical component of each worker's force, I'm going to have them just consider F1 and F2 in the blue and the yellow there to go in the other direction. Alright, so in part A, we're asked to find the tension. Now the tension is along each of these ropes. It's this force pointing away from the mass that's holding it up. Now, the tension here is not a scalar, right? So it's going to be a vector with a certain magnitude. What's a little strange is just that in part B then asks for the vertical component of each worker's force. Well, that's going to be contained in the tension unless perhaps this book is referring to tension as a scalar, which is a little atypical, but I can see why they might do that. All right, so let's write these things out. So notice for F1 on the left, this is sort of our triangle. Here's 20 degrees. It's kind of badly done. But then F1 is sort of the hypotenuse. So if I were to find, or the size of F1 is the length of the hypotenuse. So if I want to give a vector form for this force here, and again I'm going to conceptualize it going up and to the left, the x component will be the sine of 20 degrees, but it's going to be going to the left, so negative, and the y component will be the cosine of 20 degrees, but both of these are also increased by the size of that hypotenuse, so it's magnitude of F1. Likewise, F2 would be the magnitude of F2, how big it is. It's in the direction, though, of, so this is very similar, but it's going to the right and has a 30 degrees, and then cosine of 30 degrees. Alright, so since they're holding it in a certain equilibrium, the left and right components will cancel each other. Alright, so I know that F1 times negative sine of 20 plus F2 sine of 30, those would have to zero each other out. And so that will be helpful for getting a certain size. And then I would also know my other equation is that the y component, so F1 cosine of 20, it might be better to, instead of calling it magnitude of F1, just call it little a or little b or something like that to make the notation a little bit nicer. Anyway, this plus F2, the size thereof, times cosine of 30, that needs to equal 100. Great, so let's just go ahead and go about solving this system of equations. We could do it in a couple different ways. What I'm just going to go ahead and do is do it by substitution, right? So the top equation very quickly turns into that, let's just say F1 is equal to size of F2 times sine of 30 divided by sine of 20. Stick that into the second equation here, and we end up with f2 factoring out of everything. We have sine 30 divided by sine 20 cosine 20 plus cosine 30. That's all equal to 100. So we can stick this into a calculator and say, f2 is going to be 100 divided by, I might even write that as sine 30 cotangent 20 plus cosine 30. And then it'll be very quick after that to then substitute into this equation to get f1. I'm just going to pause the video and stick those into a calculator here. Great, when I stick this into my calculator, I get the magnitude of f2 as 44.648 and magnitude of f1 as 65.270. And those are the magnitudes. Now that might be what they're intending in part A with the tension, although really that multiplied by your vectors up here is really what tension should be. For the vertical component, then I would just multiply my f1 and my f2 times cosine of 30 and cosine of 20, and I would have my final result. Great, so when I plug those in, these give me my vertical components of 61.334, and these are, I guess I should use my units, be a good, I guess, physicist here. Say force is measured in pounds. And so the vertical components then should add up to 100 pounds, and they're very, very close. I just had to round in each of these cases. So that's a good way to verify that the vertical should be 100. And notice there's a little bit more in these numbers, F1 and F2 in the magnitudes. That just means that the amount of strength you have to put into pulling those ropes is a little bit more, since you are not just pulling straight up, but you are also pulling against each other. So there's a little bit of sort of wasted force in there. All right, maybe this video will help with the ideas in 80. And again, I'll just sort of say, if I were to do this in your position, I might make things easier just by calling this little a and little b or something like that to make the notation a bit nicer.